Hello again. This is part 2 of the science in equilibrium, hanging masses and otherwise that don't move. So this is static equilibrium. So I have something, maybe a ceiling, holding this sign with 2 ropes, and I'm going to try to figure out the tension in this rope, and we're on page 30. So the forces acting on this mass is the mg, and we have a tension here, and we have a tension here. Now, a lot of times these two are different, but since the angles here are the same, we can see probably that the T's will be the same, or we can prove that, but there is no need for that. I think conceptually and logically we can see that. So the T's are the same. So now I'm going to write my equilibrium statements for this one. This should be in the x direction. This T here has a component, just like I explained in the video, going to the right, and a component going to going up. In other words, this string is pulling right on this box, and it's also supporting it up. So I can say that T cosine of 35 is equal to T cosine of 35 on this side. Well, that doesn't do me any good. I can't do anything with that. In the y direction, I can see that there is a y component of this T that's pointing up, right? We don't draw components on the force diagram. That should be T sine 35 plus another T sine 35, because the T's are the same. So I can just say this is 2T sine 35 equals whatever is acting down. This is basically Newton's second law with no acceleration, equals mg. So the mass is 8, the g is 10. If we do the math here, we should get, I have the answers here, so we should get 69.74. Newtons. You just have to be careful when you're doing the division 80 by 2 sine 35 to get the T. Make sure you put this in parentheses, otherwise the calculator will divide by 2 and multiply by sine of 35, and that's not what you want. All right, let's look at number 4. Okay, number 4 is giving you the forces, and it's asking to find the angle. So again, here's mg, the pull of Earth on the object. There's a tension here, and here's tension here. Now these two tensions are 15 newtons each. So if I do the x component, so this string here to the right is pulling right and up. This one is pulling left and up. So right equals left. Well, that doesn't do me any good. I can't solve anything. In here, going up, it looks like it's T sine of theta, and there's 2 of them because the T's are equal, and that's equal to mg. Now, so this is going to be sine theta is going to be equal to 50 divided by 2 times 50, which is 100. So sine theta equals half. That should give you an angle of 30 degrees. Okay, you don't need to put that in the calculator. You've already learned that in your trig classes. 30 is a special angle. All right. Okay. Let me just scroll more. All right. For 5, we're going to try to find the angle again. Okay. It's the same concept. I don't think I need to repeat myself doing that. So I'm going to do number 6. So I have mg down here. I have a tension of 30 newtons here, and I have an equal tension of 30 newtons there. And the angles are 10 degrees. These are the angles. So I can say that, well, to the right, nothing is, the equilibrium statement to the right is not going to do me any good. It's going to be T cosine 10 equals T cosine 10. That doesn't do me any good. So now I'm going to do the y. So it's going to be T sine of 10 plus T sine of 10, component that's pointing up. So there's 2 of them, and those have to equal the mg. So this is going to be 60 sine 10 over 10 equals the mass. And you should get a mass of 1.04 kilograms. Okay. All these problems are pretty much similar, right? It's the same concept over and over. Now we're going to do somewhere the number 7 is kind of like is the same as number 6, so I'm not going to do it. I'm going to do number 8, which is a little bit different than the other ones because the angles are different. So we're going to try to find the tension here. Okay. Now I can write. Actually, yeah, that's fine. All right. So I'm going to say in the x direction, t, or I can start with the 12. 12 cosine of 10 degrees equals t cosine of 45. And you can see that I really don't need to do the vertical part to get the answer. Okay, I can just stick with the horizontal part. If I do the vertical part, the answer will probably be slightly different because that's probably not exactly 12 newtons. So t is 12 cosine of 10 over cosine of 45. Now, if you do it in the horizontal direction, we get 16.71. If we do it in the vertical direction, which has more terms, is 12 sine of 10 plus the y component of t is sine of 45 equals mg, because you have the tensions here. So mg, which is basically 14, and the t here will be about 1685, which is about similar to 1671. Okay? Now, this should have been expected to be greater than 12. And the reason is this string here makes an 80-degree angle with the vertical. This string here to the left is more vertical because it only makes 45 degrees with the vertical line. So, which means that the one on the left supports more of the 1.4 kilograms than does the one with the 80 degrees with the vertical. All right, a couple more here. We're on page 32. So if I'm looking at this, this is just maybe a ceiling holding the sign. So the tension doesn't have to extend all the way up there, but you can extend it. So the length of the string does not really mean the length of the, the magnitude of the tension. So since the angles here are the same, I'm going to say this is tension, and this is the same amount of tension. And then I have my Fg or mg. That's the force of gravity, the pull of gravity. So now in the x direction, the one on the left is pulling right, and the one on the right is pulling left. So that's going to be t cosine of 70 equals t cosine of 70. The statement does not get me anywhere. Now I have to rely on the y direction to get the tension. So the component of this left tension, the y component, is going up this way. Okay, so I'm just showing you because I don't want to keep it there. You cannot have the components in the diagram. So that looks like it's across from the 70 degrees. So that's t sine of 70, and you will get another one from the other side, also pointing up. So they have to add up to equal the mg. Okay, now we can solve. Now that's 100 over 2 sine of 70. Now when you put that in the calculator, make sure you put parentheses around here. And you should get an answer of 53.21. So that's your tension. Excuse me, I just have to open the door. All right, I'm back. All right, so let's look at B on this page. Now, the angles are different. So the tension on the left has to be bigger because the angle that this string makes with the vertical is 20 degrees. This one is a 75-degree angle. So this tension here is bigger. And you see how the length of the string has nothing to do with it. And this tension here is smaller. Make it a little bigger. Okay, so I call this on the left T1 and this one T2. Okay, I'll put the T1 on this side here. And the reason for that, I want to make my triangle here. Okay, and I have my MG. Okay, now in the X direction, I should get T2 cosine of 15 equals T1 cosine of 70. Okay. In other words, this component here of T2 has to equal this component here, okay, of T1. I mean, it's not drawn to scale, but you get the idea. Technically, this should be the same length. So this should have been smaller. And then in the Y direction, it should be T2 sine of 15 on the right side. This component here is going to be pointing up, plus this component here pointing also up. Those two, because this is in equilibrium, there is no acceleration, forces acting up have to equal the forces acting down. Now, you have a system of equations where you have to solve for T1 and T2. How you do it is your business. You can do substitution, you can do elimination, you can do whatever you want. So I'm just going to do it one way, and then you can do it any other way you want. So I'm going to isolate T2 in equation 1. So that's going to be T1 cosine of 70 over cosine of 15. And then I'm going to plug that, or this expression, into T2 here. So it should be T1 cosine of 70 over cosine of 15 times sine of 15 plus T1 sine of 70 equals 10 times 10, which is 100. Now, I can manipulate this more, so I can see a T1 common to both of these guys. I can factor out a T1, right? Now you can figure this out and do 100 divided by whatever you come up with. And that should be, what is it? 34.33. So T1 is 34.33 newtons. Now, how do I find the other force? All you have to do is maybe take this T1 and plug it into here, right? Or you can plug it back into the first equation. Don't plug it into the second. It's just, it's going to take too long. It's a lot of terms in there. So that's just algebra, so I'm not going to go over that. Okay? We're looking at problem C now. This microphone keeps falling. All right. Okay. Christine hangs from a bar supported by 2 ropes, right? So here's Christine. Okay, each making an angle of 35 degrees to the horizontal. So here's 1, here's 2. 35 is here. It's with respect to the horizontal. This is another 35. Okay? And this is your mg. Now the tension in each rope is 350, so this is, tension has to be the same in this case because the angle is the same. Okay, so tension and tension. I'm not going to label them 1 and 2. What is Christine's mass, not weight? Okay. So I'm going to say, well, T cosine of 35, this component is equal to T cosine of 35, which is this component. Okay, that doesn't help me at all. Then I do T sine of 35, this component here pointing up, because when you're pulling up like that, you're pulling left and you're pulling up. But these are just temporary, so I'm going to remove them. Okay, plus another T sine 35, which makes it 2 times T sine 35, equals the mg, or 10 times m. Now, this is going to be 700 sine 35 over 10 is the mass, and that should be in kilograms. And her mass is 40.15 kilograms. Okay. Now we're doing 44 on the, what page is that? Page 35, it looks like. All right. Dan has a mass of 60 kilograms, hangs on the rings during a gymnastics tournament. If the 2 chains are supporting Dan and the chains are directed straight up, what is the tension in each? So that should be easy. Here's the mass, which is 60 kilograms. It's 2 ropes, tension and tension equal, and is your mg. So here there's nothing happening side to side, so I have 2 tensions equals mg. So which means T equals mg, which is 600 divided by 2, which gives us 300 newtons for each rope. Number 45. 2 cables, both at equal angle with the horizontal, support a bridge with a mass of 1,200 kilograms. If the tension in each cable is 6,400 newtons, what are the angles the cables make? Oh, let's take a look. Here it is. Okay. So, same angle. Okay. All right. So here's the tension. Here's the same tension. So that's why I don't put subscripts. And here is the mg for the bridge. I think I'm going to make, both equal with the horizontal. So I'm going to stick with the horizontals. Here is theta, and here is another theta. So you can see that right and left, that's not going to do me any good because it's going to be T cosine theta equals T cosine theta. So if I do it up, it's T sine theta plus another T sine theta equals the mg. The tension is 6,400, so this is 12,800 sine of theta equals 1,200 times 10, which is 12,000. And if you solve for theta, you have to do the inverse sine eventually. You should get about 70 degrees, 69 and change, so about 70 degrees with the horizontal. Okay, 2 spring scales are holding up a mass of 26.61 kilograms. Okay, and they give you the angles that the strings, the spring scales make with the horizontal. And they give you the tension in one of them, so we need to find the tension in the other. All right, it shouldn't be too difficult. So here's one, and here's the other. So now drawn to scale again. So I'm just going to say this is the 28 degrees. Or maybe I'll draw this a little higher. There you go. And this is 42 degrees. And this is the mg. Now it looks like this one here is closer to the vertical. So the one on the left has to support more, right? So I'm just going to say that this is the T1 and this is the T2, and I'm going to make this a little bigger. Okay. and the mass is 26.61. Now I'm going to try to do this in the horizontal direction. If I can solve it in the horizontal direction, I don't need to do it vertically. So I can say that, so which one makes it 28 degrees? All right, it doesn't matter. So I'm going to say T1 cosine of 28 equals T2 cosine of 42. So okay, so 1 makes it, oh, I flipped this. So this should be 2 and this should be 1. So it says that scale 1 makes a 42 degree, yeah. So I'm just going to change this, no big deal. Okay, so I'm going to try to find the tension in scale 1. So this is basically 250 newtons. All right, so T2 is going to be equal to T1 cosine of 42 over cosine of 28. And if we do the math, 250, and make sure you are in degree mode when you're doing this stuff, okay? Cosine of 28, I got 210.42, okay? Yeah. And I could have done it vertically, but it's just too much work. I have to worry about the mg. So the equation vertically will be written as T1 sine of 42 plus T2 sine of 28 equals 266.1, which is the mg. Okay, too much work. All right, the next one. It looks like it's complicated, but actually it's not. So this string here, I'm going to say, you know what, I'm going to just go up to here. I don't have to, but I'm going to say this is the tension in string A, and this is the tension in B, okay, and this is the weight of the object. This is the mg. And that's all there is. So I'm going to write the statements in the x direction first. So I see that all of TB is going right. But for TA, I need to get this component here, which is pointing left. Now, with respect to this angle 30, this component, this x component, that's the opposite. So that should be TA sine of 30. A lot of times we always write cosine because we usually look at the angle with respect to the horizontal. I could have done it as TA cosine of 60. Now, sine of 30 and cosine of 60 are exactly the same thing. Now, if I do vertically, well, there is nothing from TB, doesn't contribute at all. Then I get TA cosine of 30 is equal to mg, right? Maybe I should have put it, I'm just going to rearrange this. So I'm going to write it as TA sine of 30, and you'll see why, equals TB. So I have two unknowns, right? And I have two equations. That's definitely doable. So I don't want to do any substitution or anything like that. So this is what I'm going to do. I'm going to do equation 1 divided by equation 2. And let's see what that gives me. So if I divide the left side by this left side, the TAs will go away, and I end up with tangent of 30, which is sine of 30 over cosine of 30. Is TB over the mg is 750. See what it says newtons here? That's the mg. You don't want to multiply that by 10. And it should be about, should be 433.01, right? Yeah. Okay. And that should do it for the sines in equilibrium. I'm done.